discovery of electron. At the end of 19th century, several scientists, including Crookes, 1879, Julius Plucker, 1889, J. Thomson, 1896, tried to pass electricity through gases. They found that electricity can be passed through gases only when a high voltage is applied at very low pressure. The experiments involving the passage of electricity through gases at low pressure were called discharge tube experiments. These experiments demonstrated the emission of certain invisible rays from cathode. These rays produced fluorescence on glass and affected the photographic plate. These rays were named as cathode rays. J. Thomson studied the properties of these rays, which led to the discovery of the electron. A discharge tube consists of perfectly leak-proof glass tube with metal electrodes fused in it. The tube is evacuated by connecting it to a vacuum pump. The tube is filled with the gas understudy. The pressure of the gas in the tube is reduced to about 10⁻² to 10⁻³ mm with the help of vacuum pump. And a very high voltage, about 5,000 to 10,000 volts, is applied to the electrodes. Electric discharge occurs between two electrodes, and the gas in the tube begins to glow. If high vacuum is created within the tube, the glow is replaced by faint luminous rays, which produce fluorescence on the glass at the end far from the cathode. The rays starting from the cathode and go away from it at right angles in straight lines are called cathode rays. Properties of cathode rays. 1. Cathode rays travel in straight lines from the cathode and cast shadows of metallic objects placed in their path. 2. Cathode rays cause mechanical motion of a small pinwheel placed in their path. Hence, they possess kinetic energy, and must be the material particles. 3. Cathode ray produce fluorescence, that is, a glow, when they strike the glass wall of a discharge tube. 4. Cathode rays, when strike the metal foil, it becomes red, and starts glowing. 5. Cathode rays produce X-rays when they strike a metallic target. 6. Cathode rays are deflected by the electric as well as magnetic field, indicating that they are streams of minute particles carrying negative charge. 7. Cathode rays produce ionization of gases through which they travel. Charge to mass ratio of electrons. British physicist J. Thomson measured the ratio of electrical charge, E, to the mass, m, of cathode ray particle by using specially designed cathode ray tube. It involves the application of electrical and magnetic field perpendicular to each other, as well as to the path of rays. Thomson observed that the extent of deviation of the particles from their path in the presence of electric or magnetic fields depends upon the voltage applied across the electrodes and opposing magnetic field strength. In absence of electric and magnetic fields, cathode rays originate at cathode, pass through a hole in anode, and strike the ZNS screen at Y. When electric fixed strength is applied, cathode rays are deflected towards positive electrode, and strike the screen at point X. While instead of electrical field, cathode field is applied at right angles to the electrical field, cathode rays are deviated in opposite direction and strike the screen Z. During the experiment, first the cathode rays are subjected to electric field of appropriate voltage, so that cathode rays deviate from the path, and, instead of at Y on the screen, strike at X. Now, along with the electric field, cathode rays are also subjected to magnetic field of field strength H, such that the effect due to electric field is compensated by magnetic field, and cathode rays are once again brought back to the original point Y. Thomson repeated the experiment with cathode rays of different energies and strengths of electric field, or magnetic fields. He was able to determine the value of upon, i.e., ratio of charge to mass, of particles of cathode rays as E upon m is equal to 1.758820 x 10 raised to coulomb per kg. Here, m is the mass of particle of cathode rays in kg, and E is its charge in coulomb. The particles are negatively charged, and, therefore, the charge on the cathode ray particle is represented as -E. As a result of several experiments, Sir J. Thomson showed that the value of upon for a cathode ray particle was the same irrespective of the nature of gas used in the discharge tube, and the nature of material of which the cathode was made. This proved that all the constituent particles of cathode rays are identical. This also proved that these particles are the universal constituents of all the atoms of all matter. Charge on the electron. Scientist R. A. Millikan established a method known as oil drop experiment to determine the charge on electrons. He found that the charge on the electron is equal to -1.6 x 10⁻19 coulomb. Accepted value of electrical charge is -1.60 to 2 x 10⁻19 coulomb. By knowing charge and upon value, it was possible to determine the mass of electron. Where E is electronic charge and m its mass is equal to 9.1094 x 10⁻31. Mass of electron is found to be 1 upon 1830 h, the mass of an atom of hydrogen of an atom of hydrogen. The existence of subatomic particle, electron, was further supported by flow of electricity, which is a flow of electrons through conductor. Discovery of beta particle, emitted unstable radioactive nuclei, also proved existence of electron, as beta particle was proved to be the same electron. Hence, an electron is a subatomic particle which bears unit negative charge. That is 1.6022 x 10⁻19 coulomb, and has a mass of 9.1094 x 10⁻31 kg. An atom is electrically neutral, and contains negatively charged electrons. Hence, it was believed that an atom must also contain some positively charged subatomic particle to neutralize the charge on electron. Hence, attempts were made to dicover a positively charged particle.